Alright, so today we are looking at, first off we're looking at weyl formulas. We might be able to move on to the other one, which I don't even remember. I also don't know why I decided to try to make the apostrophe the S. Alright, and we start out with a lemma, which is that our Q is the sum over the weyl group of the sine of our sigma times its eta of sigma with delta. And we can prove this directly, but we can use a formula from before, where if lambda is 0, then by our old formula, the character of lambda is eta 0, and so by our old formula, Q convoluted with the character of lambda being the sum over the weyl group. My chair is going to be loud, I'm sorry about that. Of the sine of sigma times epsilon of sigma of lambda plus delta. We are done. Man, one sec. Alright. So up next we have, well, Weyl's theorem. Weyl's formula here. Let lambda be in lambda plus. Then summing along sigma in the weyl group of the sine of sigma times eta of sigma acting on eta of sigma with delta, convoluted with the formal character of lambda, is the sum over the sigma in the weyl group of the sine of our sigma times eta of sigma of lambda plus delta. And this is by the previous formula, which I wrote again up there, and the lemma. And so this says that we can calculate the formal character of lambda as a quotient of two simple alternating sums in said lambda. But it's usually not as fast as Freudenthal's method. But we can get from this formula a very useful formula for the dimension of V lambda. So we can use this to find the dimension of V lambda, which we denote as the degree of lambda, and then it's clear from that the degree of lambda is the sum over mu in pi lambda of mu. I'm sorry, this is getting unreadable. I need to just skip to a new line here. The degree of lambda being the sum over mu in pi lambda of m lambda of mu. Since V lambda is the direct sum of weight spaces, this is just, however, is just the sum of coefficients in the formal sum of m lambda mu over mu with e mu. It's very weirdly written here in z of our lambda. And so in a function notation, this is the sum of values of the character of lambda. Now recall, note, I guess we better note the subalgebra x naught in x generated by the characteristic functions eta lambda for lambda and lambda. So the homomorphism v from x0 to f, assigning to each f and x naught the sum of its values, is defined. So now we need to compute v of the character of lambda as a function of lambda. But apply it to an alternating sum, which is our sum of sine lambda e epsilon sigma delta. So our like we saw that sine of sigma epsilon sigma delta for sigma being in the vowel group, but since this is an alternating sum, v is just going to give 0. So we got to go take a more indirect route. We're going to abbreviate the sum over the sine or sigma times epsilon of sigma of lambda plus delta by omega of lambda plus delta for any lambda in lambda plus. Now we see that the assignment from epsilon lambda to lambda plus alpha times epsilon lambda for fixed alpha extends to an endomorphism. Well, del, I don't know what to call this fancy d, dA of x naught, which is actually a derivation. The endomorphism, if it'll scroll, delta as the product of positive roots delta alpha d alphas is not a derivation in general, but may be thought of as a differential operator. Now, Weyl's formula reads omega of delta convoluted with the characteristic function of lambda, the formal character of lambda, is omega of lambda plus delta in the sense we wrote above. Now here, this omega of delta is the weyl function, which is epsilon of negative delta convoluted with the convolution over positive roots of our epsilon alpha minus 1. Multiply this expression by the formal character of lambda, and apply our faux differential using the product rule, then by v. Since the v epsilon alpha minus 1 is going to be 0, we are left with v of the faux differential of the weyl function of delta times v of the formal character of lambda, which by Weyl's formula is v of faux differential of omega of lambda plus delta. So we can express the degree of lambda as v of the formal character of lambda as a quotient. Now we see that v of our faux differential of epsilon of delta is the product over our positive roots of the form of delta with alpha. Similarly, v of the faux differential of epsilon of sigma delta is the product over our positive roots of sigma delta with alpha, which is the product over positive roots. Delta, we can just shift the weyl thing over to the other side like that. As the number of positive roots sent to negative roots by sigma inverse is L of sigma inverse, which is, we saw, just the length of sigma, which I believe is just the number of distinct reflections is generated. It's something like that. It's basically the length of the generating of this from reflections, so that makes sense. So this is just the sine of our element of the weyl group times the product over the positive roots of delta formed with alpha, where we recall that the sine of delta is as if it's in the symmetrical, as if it's a sine of a symmetrical group, -1 to the length of sigma. That's v of the faux differential of omega of the delta is the sum over the elements of the weyl group of the sine of our reflection times v of delta of epsilon sigma delta, which is the sum over sine in W. Then right here, the sine of sigma squared, which I think is now just 1, going to disappear, times the sum over the positive roots of the form of delta with alpha, that's product, not a sum, which is the cardinality of the Weyl group. Yeah. Yeah, because the sine square is always going to be 1, this is just going to, this term on the left is just going to count the number of elements in the Weyl group, essentially. And we can apply this at omega of lambda plus delta, gives the same cardinality of the Weyl group. I should use weyl notation, times over the positive roots of this lambda plus delta with alpha. Thus, we get a corollary. Don't know why it's having so much trouble scrolling down all of a sudden. Let lambda be a dominant root, dominant weight in lambda plus. Then the degree of lambda is the product for positive roots of lambda plus delta with alpha over for the positive roots of our just delta with alpha. Now we want to do an example computation or two with this, but let's do some pre-work first. I'll do that on a new page, it looks like. And we note that after multiplying the numerator and denominator by the product or positive roots of 2 over the form of alpha with itself, we get that the degree of lambda essentially is the same thing, except we're going to replace the round brackets with angle brackets. With that term, we multiply the top and the bottom, being a kind of conversion factor that's the same for both. And this is a quotient of integers, is the key idea here. But we recall that lambda plus delta, angle bracket with alpha, we have this idea of, we set up way before in like one line the idea of a dual root, which is just set up so we have this following equation, where this is the dual. Now, since the dual of a base, I believe component-wise, is a base of the dual of our root system, we can write the dual of our root as the sum of our CI alpha to the alpha I dual from our root, from our base, I believe, giving us that I'm going to write this on a new line again if this thing will scroll. The angle bracket of lambda plus delta and alpha we see at the top there is the sum over ci alpha of our angle bracket of lambda plus delta with the component alpha I, which is the sum for ci alpha of our mi plus 1. That's not really looking like an m, is it? Mi plus 1 for lambda being split up. These m come from the splitting up lambda into mi lambda I. So we only need to compute the integers ci alpha. Now let's look at an example. For our Weyl algebras of the type A1, our lambda 1 is half of alpha is our delta. So the degree of lambda is m plus 1. And lambda being m of lambda 1. Now, consider rank 2 with our lambda being m1 lambda 1 plus m2 lambda 2. For A1, for A2, the positive roots are alpha 1, alpha 2, and of course their sum. The denominator then reads 1 times 1 times 2, with the numerator reading m1 plus 1 times m2 plus 1 times m1 plus m2 plus 2. The calculation is similar. For B2 and G2. And so take alpha 2 be short for B2 and alpha 1 short for G2 to keep things consistent. Then, so A2 is going to be 1/2 of m1 plus 1, m2 plus 1, m1 plus m2 plus 2. Our B2 is going to be 1 over 3 factorial, which is 6, of course. M1 plus 1, M2 plus 1, M1 plus M2 plus 2, and then 2M1 plus M2 plus 3. And for G2, our term out front is 1 over 5 factorial. And then we have m1 plus 1, m2 plus 1, m1 plus m2 plus 2, m1 plus 2, m2 plus 3, m1 plus 3, m2 plus 4, and then finally 2m1 plus 3, m2 plus 5. And we see at this, we see for G2, the degree of lambda 2 is 14. As lambda 2 is 3 alpha 1 plus 2 alpha 2. The highest root. We recognize v of lambda 2 as the module for the adjoint. The degree of lambda 1 is 7. And here v of lambda 1 is C0, which is the trace 0 subspace of the Cayley algebra that we saw last time. And then how long has it been? Okay. Up next, we are going to be closing off our formula talk with Steinberg. And this is to calculate an explicit formula for the number of occurrences of v lambda in the tensor product. All right, here, the goal is the number of occurrences of v lambda in v lambda prime tensor v lambda double prime. Because of Weyl's theorem on complete reducibility of finite dimensional L modules, if lambda prime and lambda double prime are in lambda plus, we can write v lambda prime tensored with v lambda double prime as a direct sum of certain v lambda, each occurring n lambda times, of course being 0 if it does not actually occur. In particular, the formal character of the tensor product equals the sum over lambda in lambda plus of n lambda times the formal character of lambda. Which we showed is equal to the character of lambda prime convoluted with the character of lambda double prime. Thus, we can just write this out explicitly, that the character of lambda prime convoluted with the character of lambda double prime is the sum of n lambda times the character of our lambda. as before. We're keeping our omega abbreviation from before. So multiplying both sides by omega of delta and using weyl's formula for lambda double prime and lambda, we get the character of lambda prime convoluted with omega of lambda double prime plus delta is the sum over our roots for the count of those roots times omega of lambda plus delta. Next, we write on a new page, write out the character of lambda prime, formal character, as the sum over mu of m lambda prime of mu times eta mu, and replace m lambda prime mu by its value in Costant's formula. We then get that the sum over mu times the sum over sigma in the Weyl group of the sign of our reflection, composite reflection from the Weyl group times p of our mu plus delta minus sigma of lambda prime plus delta, all scaling epsilon mu convoluted with omega of lambda double prime plus delta is equal to the sum over our lambda of n of lambda times omega of lambda plus delta. And, by the explicit form of omega of lambda double prime plus delta, we get, I'm going to write this on a new line because I'm scared. We sum over mu, we sum over sigma in the Weyl group, and we sum over taf in the Weyl group of the sign of the composition of sigma and taf times p of mu plus delta minus sigma of lambda prime plus delta scaling eta of taf of lambda double prime plus delta then plus mu is equal to the sum over lambda times the sum over sigma in the Weyl group of our scaling factor of n, counting lambda, times the sign of our sigma times epsilon of sigma times lambda plus delta. Now to compare these sides, we need to do a change of variables. So on the right hand side, we want to replace lambda by nu, where sigma of lambda plus delta is nu plus delta to get the sum over nu, the sum over sigma in the file group, of the sine of sigma times n of sigma of nu plus delta minus delta times epsilon of nu plus delta. And on the left-hand side, we replace mu by nu, where taf of lambda double prime plus sigma then plus mu is equal to nu plus delta, to get, and then I'm going to write this on a new line, the sum over nu, sum over sigma in the vial group, then sum over taf in the vial group, of the sine of the composition of sigma and taf times p of v plus 2 times our delta now, minus sigma of lambda prime plus delta minus taf of lambda double prime plus delta times epsilon of v plus data. Delta. Don't know why I called it data. Now let nu be dominant. Then sigma nu plus delta minus delta is not dominant unless it is just the identity. Thus n of sigma of nu plus delta minus delta is 0 unless sigma is 1, which means the coefficient of epsilon of nu plus delta in our right-hand side term, in our new right-hand side term of the above, is just n of nu. Thus, we have proved this gives us for free a theorem, which is Steinberg. We're going to let lambda prime, lambda double prime be in lambda plus. Then the number of occurrences of v of lambda for lambda, of course, in lambda plus in the tensor product of v lambda prime tensor v lambda double prime is given by summing over sigma and taf in the vial group, the sine of their composition times p times lambda plus 2 times delta minus sigma lambda prime plus delta minus taf of lambda double prime plus delta. And like before, this is an explicit form, but given that we iterate over the vial group twice for large vial groups, this is not going to be a very fun thing to calculate. Alright, and then I'm going to look over if we need to go over the appendix, and then we'll be going over the Chevalier algebras and groups, which I don't know if this is the last chapter of this or not, but we're closing in on like the end of the pre-group talk, so that's exciting, you know? Look forward to that. Thanks for watching, I guess.